Dead men tell no tales, but their ships speak volumes. Welcome to the Cursed Compass, where we explore the darkest maritime mysteries. In 1884, deep in heavy fog on the open ocean, the British steamer Rumney collided with a French cargo ship named the Frigorifique. Convinced their severely damaged vessel was about to sink, the French crew abandoned the Frigorifique and scrambled aboard the Rumney for safety. But the Frigorifique did not go down. It was equipped with a highly compartmentalized, heavily insulated cargo architecture designed to trap cold air. Those exact same sealed, buoyant chambers kept the crippled hull afloat. Left to drift blindly in the fog, the abandoned ship became a maritime hazard. It eventually circled back, striking the Rumney a second time with such force that it sank the British rescue ship. While this event reads like a ghost ship anomaly, the Frigorifique was actually a mechanical prototype. It represents the historical window when engineers first attempted to control thermal dynamics on the open water. Look at this 3D map of modern maritime traffic. The highlighted lines show the thousands of active refrigerated shipping lanes connecting continents today. It is an invisible grid of temperature-controlled logistics operating across the oceans. Mastering the ability to transport perishable biological cargo across the equator required overcoming massive thermodynamic barriers. Engineering that solution allowed isolated agricultural regions to serve as the primary food sources for distant industrial centers. In 1869, shipping meat meant packing carcasses in a mixture of salt and ice. The limits of this passive cooling were absolute: the size of the ice block, the ambient climate, and the rigid distance a ship could cover before the ice completely melted. To break these geographical constraints, inventors turned to active chemical compression. By 1876, Charles Tellier retrofitted the Frigorifique with a methyl-ether plant, and a year later, Ferdinand Carré successfully deployed an ammonia-based refrigeration system on the Paraguay. The challenge was powering these compressors at sea. Look at the clipper sailing ship Dunedin, refitted in 1881. You can see a steam funnel placed unusually right between the fore and main masts. That exhaust stack belonged to the refrigeration plant. This diagram outlines the Bell-Coleman system. A dedicated steam engine burned coal to drive a mechanical compressor. High-pressure air was driven into a chamber and released into the cargo hold. Expanding rapidly, it absorbed heat, lowering the temperature by 40 degrees. Relying on this continuous thermodynamic cycle, the Dunedin maintained a freezing environment through the tropics for a 98-day voyage, carrying nearly 5,000 frozen mutton and lamb carcasses, alongside kegs of butter and poultry. The cargo arrived in London entirely unspoiled. After covering the steep engineering and coal costs, the voyage yielded a 4,700-pound profit. Mechanical freezing at sea was a proven, scalable commercial enterprise. With the economic model validated, shipyards in Scotland and modern England began mass-producing and retrofitting these cargo vessels. By 1910, the British company J&E Hall had standardized the industry, installing over 1,800 carbon dioxide-based refrigeration machines across the global fleet. Concurrently, the United Fruit Company began rapidly expanding its logistics network, commissioning a specialized group of vessels in the early 1900s that would become known as the Great White Fleet. The name served a specific thermodynamic function. The massive steel cargo hulls were painted stark white to reflect incoming solar radiation, a passive thermal defense that reduced the daily workload on the internal mechanical compressors. To maximize efficiency, these ships functioned on a dual-purpose economic model. They acted as cruise liners carrying heavy passenger loads down to Central American ports and returned to the United States carrying light, perishable bananas in their actively cooled holds. This synchronized transport model funded immense growth. The United Fruit Company amassed a fleet of roughly 85 ships, effectively monopolizing the Central American fruit trade by controlling the cold chain distribution network. Profit margins in this era were entirely dictated by cargo volume minus coal consumption. Shipbuilders were forced to design vessels that balanced heavy, space-consuming insulation materials with the maximum possible internal volume for paying freight. When World War I erupted, military command faced an immediate logistical bottleneck. Deploying millions of troops in Europe required a massive, sustained supply chain of fresh provisions shipped safely across the Atlantic. The United States Maritime Commission addressed this by directly requisitioning existing commercial infrastructure. They seized highly efficient passenger and refrigerated cargo liners straight from the United Fruit Company, including the advanced Mizar-class vessels. By World War II, these acquisitions became incredibly aggressive. In April 1943, U.S. Navy officers literally intercepted the commercial ship Ulua as it approached the Golden Gate Bridge, boarding it and immediately converting it into the military store ship USS Octans. The Navy needed far more capacity, ordering 41 new refrigerated ships. However, integrating complex compressors, extensive insulation, and heavy power generation into a ship's hull is a slow, exacting process. Because of this specific mechanical difficulty, only 2 newly built vessels were delivered throughout all of 1944. Global supply chain mastery elevated the refrigerated ship to a strategic military asset, as vital to modern warfare as the munitions it traveled alongside. The limits of central cargo hold refrigeration eventually gave way to a modular solution. Modern logistics rely almost entirely on the refrigerated 20-foot equivalent unit, or TEU, where the cooling machinery is attached directly to the rear of the individual shipping container. Moving thousands of these active units on a single vessel requires immense power generation. A modern container ship operates as a floating power plant, distributing a 440-volt alternating current grid directly to every individual container bay. Each TEU plugs into a standalone electrical circuit with its own breaker switch. If a compressor fails mid-voyage, engineers can isolate, unplug, and repair the single defective unit without compromising the temperature of the surrounding cargo. Containers on the upper deck vent waste heat freely, but packing active refrigeration units inside the hull creates a thermal trap. To solve this, a fresh water loop circulates past the buried containers, absorbing the heat. Heat exchangers then transfer this energy into the ocean. For highly sensitive, high-value biological cargo like whole blood or caviar, the industry employs specialized TEUs equipped with precise dual compressor systems to guarantee exact temperatures and zero failure rates. By attaching the cooling plant to the box rather than the ship, engineers eliminated the thermodynamic bottleneck of the massive central hold. The entire maritime cold chain became a highly scalable, decentralized power grid. When we look at the global data today, there are roughly 38,000 registered merchant ships operating worldwide. Only about 920 of those are structurally designed exclusively as dedicated refrigerated cargo ships. Following the corporate precedents set by early fruit monopolies, the vast majority of these specialized vessels operate under flags of convenience. They are primarily registered in Panama and Liberia to bypass stricter shipping regulations and taxes. While the number of dedicated reefer ships is shrinking, the total volume of refrigerated ocean freight is continually rising. The self-contained TEU decoupled the cold cargo from the vessel type. Today, any standard multi-purpose cargo ship equipped with sufficient onboard generator capacity and standard electrical outlets can haul frozen biological material across the equator. The modern global diet is a mechanical achievement, the direct result of a 150-year engineering war against ambient heat and marine thermodynamics.